In this video, we will discuss the wave equation. If f is a function of position x and time t, we say that it satisfies the wave equation if f satisfies this equation. So this is called the wave equation. And if f is a solution to this, then it can be called a wave function. Though usually in physics that's used in the context of quantum mechanics. We see that the wave equation involves a second order spatial derivative and a second order time derivative as well. If we denote spatial derivatives by a prime and time derivatives by a dot, then we can write the equation as f double prime equals 1 over v squared f double dot. It turns out to be fairly easy to get the solution to the wave equation. Any function of the form f of x minus vt is a solution to the wave equation. This includes x minus vt the whole squared, e to the x minus vt, or x minus vt plus e to the minus x minus vt the whole squared. Any function you can think of, as long as the combination x minus vt occurs together everywhere. So you can't have x and t appearing separately. Whenever they appear, they have to appear in that combination of x minus vt. This seems almost too general. Let's see how we can show this is true. We first define a new variable u equal to x minus vt. Then our function is simply f of u. We now calculate the various derivatives. If we calculate f prime, that is the derivative of f with respect to position, we can apply the chain rule and rewrite that as the derivative of f with respect to u times the derivative of u with respect to x. We leave the first part alone, just derivative of f with respect to u. And the second term, we recall what the definition of u is, and we see that the derivative of u with respect to x is just 1. And so we get that f prime is just partial of f with respect to u. Once we have f prime, we can calculate f double prime. This is the second derivative of f with respect to x. So in other words, we are taking first one derivative of f with respect to x and then another derivative with respect to x. But we already know that f prime is the same as partial f partial u, so we can plug that in. And again, we can use the chain rule to rewrite this derivative with respect to x as a derivative with respect to u times the derivative of u with respect to x. Here we can see that we have one derivative with respect to u acting on another derivative with respect to u. So we get a second derivative of f with respect to u. And we already know that partial u partial x is just 1. Similarly, we can now calculate f dot, that is the derivative of f with respect to time. Again, using the chain rule, we can rewrite this as partial f partial u times partial u partial t. But looking at the definition of u, we see that partial u partial t is just minus v. So f dot is minus v times partial f partial u. If we now calculate the second derivative of f with respect to time, f double dot, we can use the same tricks. This is 2 time derivatives in a row. First one is already known. It's minus v times partial f partial u. And now we can write the second time derivative, again using the chain rule, as a derivative with respect to u times the derivative of u with respect to t. Continuing, in this first term, we see that v is a constant, so we pull it out, and we end up with a second derivative of f with respect to u. And then looking at this term partial u partial t, we can replace that with minus v. But minus v times minus v is plus v squared. So this is what we end up with for f double dot. The boxes summarize our results so far. Putting it all together, we can check that f does indeed satisfy the wave equation. Plugging in for f double prime and f double dot, we see that, yes, this equation is satisfied. And the only thing we ever required of f was that it be a function of the combination x minus vt. Similarly, you can go through and show that x plus vt is also a valid combination, and that any function of x plus vt will also satisfy the wave equation. What is the effect of this combination x minus vt being in the function? What do the solutions look like? Let's consider a pulse function as a function where you have f of x, and at x equals 0, the function peaks and it falls off on either side. If we replace x with x minus vt, we get a new function, which we're calling g, which is a function of both x and time. What happens as time passes? We know that the function peaks when its argument is equal to 0. Now that our argument of the function is x minus vt, we have to look for when this combination is 0. At t equals 0, we can see that x equals 0 is where this argument as a whole goes to 0, and so that will be where the peak is. So this tells us, okay, at t equals 0, the peak is at x equals 0. But what about at later times? For example, at t equals 2 seconds, if v is 2 meters per second, since the peak is where x minus vt equals 0, that implies x is equal to vt at the position of the peak. And plugging in for v and t, we see that the peak has moved to x equals 4 meters. Here's a snapshot at t equals 0, and here are 2 subsequent snapshots. And you can see that as time passes, the pulse moves to the right. So replacing x with x minus vt gives you a function with the same shape, but now that one that moves to the right as time passes. What about if we had x plus vt? This describes a pulse traveling to the left. You can see that now as time increases, x will have to decrease in order for the combination x plus vt to be constant. We have shown that any function of the form f of x minus vt or f of x plus vt will satisfy the wave equation. But this is almost too many options. We will specialize to studying sinusoidal waves. One of the reasons for this is that it can be shown that any function, no matter how complicated, if it is continuous, can be built up out of combination of various sines and cosines. So if you know how the sines and cosines behave, you can extrapolate that to figure out how more complicated waves behave. So in this course, we will focus on looking at how sinusoidal, so sine or cosine waves behave. Thus, if we're looking at some y, which is a function of x and t, we can write a general sinusoidal solution of this form. If the k here is just a constant, if we multiply that through, we get y naught times sine of kx minus kvt, and we can define kv as omega. We can take a snapshot of the wave at a given moment, say t equals 0, and ask where the peaks of that function lie. Since we are looking at t equals 0, the function simplifies to just y naught times sine kx. For the sine function, we see that the peaks will be when kx is equal to pi over 2, or pi over 2 plus or minus 2 pi, or pi over 2 plus or minus 4 pi, and so on, which we can write as x equals pi over 2k plus or minus 2 pi n over k, where n is any integer. We notice that the space between the peaks of the function is 2 pi over k. You can see that here from the 2 pi over k times n. This space between the peaks at a given moment in time is called the wavelength, which we denote by lambda. K is called the wave number. The wavelength is measured in meters, and the wave number is measured in radians per meter, and they are connected by this formula. Similarly, instead of holding time constant, we can hold our position constant and ask when at that position do we see peaks of the wave function. If we look at x equals 0, our function simplifies to y naught times sine minus omega t. This is what we see if we plot y as a function of time at a given position. The peaks in this case will occur when minus omega t is equal to either pi over 2 or pi over 2 plus or minus 2 pi, pi over 2 plus or minus 4 pi, and so on. We can rewrite this as t equals minus pi over 2 omega plus or minus 2 pi n over omega, where n is any integer, positive or negative. The time between the peaks at a given point is given by the time period, capital T, which is 2 pi over omega, which we can see from here. T is the time period measured in seconds. F is 1 over the time period. This is the frequency, which is measured in hertz or cycles per second. And omega is the angular frequency, which is 2 pi over t or 2 pi times f, and is measured in radians per second. Summarizing what we have so far, a general form of the solution is y equals y naught sine of kx minus omega t. The time period t is 2 pi over omega or 1 over f. The wavelength lambda is 2 pi over k, where k is the wave number. The time period is the time between peaks at the same spot. The wavelength is the space between peaks at the same time. In this case, because we have kx minus omega t, as t increases, x also has to increase if we are following a peak on the wave. And so we say that the direction of propagation of the wave is plus I hat, that is in the positive x direction. What about the speed of propagation? Well, we have seen that if we wait at a particular spot, a pulse will pass by, and then after waiting a time t, another pulse will pass by. And if we look at the distance covered divided by the time, we know the distance between the pulses is lambda, and the time between the pulses is t. So we get the speed is lambda over t, which we can rewrite as lambda times f, or 2 pi over k times f, or omega over k. All these are different ways of expressing the speed of the wave. We notice most easily from lambda times f that if the speed of the wave is constant, then as frequency increases, lambda decreases, and vice versa. In electromagnetism, this means that high frequency radiation, electromagnetic radiation, has a very small wavelength. So X-rays and then gamma rays have extremely small wavelengths. The electromagnetic spectrum spans a huge range of frequencies, and visible light is only a small part of this. If we look at it in terms of wavelengths, radio waves can be on the order of kilometers long, going down to a few meters. Microwaves are in the range of some centimeters. Infrared, you have 10 to the minus 4 meters. Visible light is a very small range on the order of hundreds of nanometers. So in other words, 10 to the minus 7 meters. And then once you go beyond visible light to the shorter end, you have ultraviolet, and then X-rays, and then gamma rays. There is no clear demarcation between any of these categories. This is why sometimes you will hear people talk about hard ultraviolet and mean the same thing as soft X-rays. It's a very porous boundary. Similarly, hard X-rays could be soft gamma rays, and so on. And again, we notice that as we go to smaller and smaller wavelengths, we go to higher and higher frequencies, reaching 10 to the 20 hertz. One final point about the speed of a wave. If we consider a wave on a string, here I'm going to excite a pulse on the string and look at the motion of the particles on the string. You can see that the particles themselves only move up and down. However, there is a shape of a pulse, and that shape is what moves to the right. This applies to electromagnetic waves as well. The fields, the electric and magnetic fields, already exist everywhere. And at any given point, the fields oscillate. They themselves do not travel anywhere, but the pulse of excitation in the fields is what travels, and the speed of the pulse is what we call the wave speed. Depending upon what a wave is propagating in and whether there are changes in medium or boundary conditions, different things can happen. For example, if I fix one end of the string, look at what happens when I send a pulse. You can see that when it hits the fixed end, it reflects and also goes upside down. If instead of a fixed end, I have a loose end, we see that there is again a reflection, but this time the wave does not invert until it hits a fixed end. One final bit about terminology. We have been looking at waves of the form y equals y naught sine kx minus omega t. There's nothing particularly sacred about this. We could use a cosine instead, and we could add an initial phase. So let me write this entire argument inside the sine function or cosine function is called the phase phi. It basically tells us at which point in the oscillation we are. Are we at a peak? Then the phase must be pi over 2 or something similar to that. Are we at a minimum? Then the phase must be minus pi over 2. Is y equal to 0? Then the phase must be either 0 or pi. We now see why phi naught is called the initial phase, because at t equals 0 and x equals 0, the overall phase becomes equal to phi naught. And remember, phi naught simply says with what condition are we starting? Are we at the origin at t equals 0 with no movement, at maximum amplitude, at minimum amplitude, and so on? Those different possible starting conditions determine what the value of phi naught is.